Welcome to second year. Myself, Dr. Narendranath Pathak, Professor of the ECE Department. In the first year, we have learned several subjects which are mainly basic science related subjects. In the second year, you will learn several departmental subjects. Among those, this subject named as electronic device with code EC301 is one of the important subjects. Here fundamentals of semiconductor physics and application of semiconductor materials are discussed. Before this, previously in the university syllabus, basic electronics was there in the second semester. Later on, this subject was removed by the university and one subject named as solid state device was introduced in the third semester. Once again, that subject was also removed by the university, and now in place of two subjects, that is solid state devices and basic electronics, this subject was introduced by the university. Now if you go through the routine, then you will find 3 allotted lecture classes are there per week base, and the credit of this subject is 3. If you go through the syllabus, then you will find the total syllabus is divided into 4 modules. Module 1, it will take 6 lecture hour. Module 2, 10 lecture hour. Module 3, 6 lecture hour. And module 4, it is 10 lecture hour. That means to cover all the components of this syllabus, or to cover the full syllabus, total 32 lecture hours are required. So now I will discuss the syllabus of this subject. So if you go through the module 1 syllabus, then here you will learn the energy band and current carriers in semiconductor. Here you will learn bonding forces in solids, energy band theory in crystal, different materials classified depends on their electrical nature, that is metals, semiconductor, insulator, Fermi level, different semiconductor materials, those are intrinsic and extrinsic semiconductor, concept of holes, carrier concentration, mobility, diffusion and drift of carriers, different semiconductor related equations, those are continuity equations, Poisson equations, then injected minority carrier charges, recombination and generation of charge carriers. This is all about the module 1 syllabus. Now we will discuss the module 2 syllabus. In this particular one, you will find the application of semiconductor materials. So under this module, first you have to learn PN junction, that is the physical description of PN junction, basic device technologies for fabrication of a PN junction, IV characteristics and small signal switching model, different breakdowns, that is avalanche breakdown, Zener breakdown, then different diodes, Zener diode, Schottky diode, and after that once again the application of a semiconductor material, that is important one, that is BJT, bipolar junction transistor. Here you have to learn the basic construction, IV characteristics, Eversman model. In module 3, once again you have to learn the application of semiconductor material, and here you have to learn MOSFET. But before MOSFET, I will teach you the FET. FET is what? FET is field effect transistor. Now After that FET, the second one is MOSFET, metal oxide semiconductor field effect transistor. MOS capacitor, CV characteristics, then IV characteristics, small signal model of MOS transistors are discussed in this module. Module 4, it is focused on two sections. First one, that is optoelectronic devices, and second one, that is IC fabrication. Under this optoelectronics, you have to learn the optical absorption in semiconductor, photovoltaic effect, solar cell, photoconductor, photodiodes, twin photodiodes, avalanche photodiode, phototransistor, LED, laser, and then the IC fabrication technique. So here under this IC fabrication technique, you have to learn different fabrication processes, that is oxidation, diffusion, ion implantation, photolithography, etching, chemical vapor deposition, sprouting, twin tube CMOS process. So this is all about the syllabus of this subject, electronic devices. Now if you consider the reference book, here you find several books related to this. So these books are also available in our library. You may consult any of these books. Lastly, you have to learn the course outcome of this subject. Course outcome, that means after the completion of this syllabus, what you have to learn. That is CO1, that is differentiate the conduction techniques in semiconductor material. CO2, analyze characteristics of semiconductor diode and solve related problems. CO3, analyze characteristics of bipolar transistor. CO4, analyze characteristics of MOS transistor. CO5, differentiate between different optoelectronic devices. So after completion of this discussion, I will start some fundamental related to this subject. So here I will discuss the structure, that means how the atoms inside the materials are arranged. Depends on that particular one, the properties of the materials are also different. So if we consider the atomic arrangement inside the solid, then solids are mainly classified into three major types. What are those? Amorphous, polycrystalline, and crystalline. Already I told you that here you have to learn how the atoms inside the crystals are arranged. So first I will discuss the amorphous one. In the amorphous one, you will find that the atoms inside the crystal are not having a well-defined structure. It is formless. There is no such a recognizable long-range order in the position of atom inside the material. That means atoms inside the metals are haphazardly arranged. So in figure 1, you will find the atomic arrangement inside the crystal. Secondly, the polycrystalline structure. Here in the polycrystalline structure, you find several zones are there. Inside the small zone, you find some definite structure, but it is not uniform throughout your structure. So here in the figure B, the polycrystalline structure is described. Now lastly, the crystalline structure. In the crystalline structure, you find that the atoms inside the crystals are arranged in a defined periodic structure, and that particular crystalline structure is called as a lattice. So the figure 3, it is the crystalline structure of the material. So depending on atomic arrangement, these three classifications are made. Now after this, once again I will discuss some fundamental related to this subject. What is that? Though it is not included in your syllabus, but I think it is very important to know the applications of semiconductor materials when you will study the optoelectronic devices. Then you find this knowledge is important to understand the mechanism of optoelectronic devices. So that particular one is the Ec diagram. Ec diagram is what? Energy versus momentum diagram. So if you consider the energy inside the any crystal or semiconductor material, then if we consider the density of states along x-axis and along y-axis, if we consider the energy, then you will find depends on the energy band, two bands are there, that is the conduction band and the valence band. The difference between these two energy band is called the band gap, or it is the forbidden energy gap. For silicon, which is a popular semiconductor material, it is 1.11 electron volt. If you consider the second one, that is germanium, for that it is 0.67 electron volt. Now here you find in this particular Ec diagram, you find the conventional electron energy increases in the upward vertical direction. But if you consider the whole energy, then that whole energy increases in the downward vertical direction. Normally the whole exists temporarily in the valence band. In the valence band, electrons are there. If the electrons are removed from the valence band, then the vacancy of that particular one is nothing but the hole. So if we consider the p-type material, then in the valence band you have to find the permanent existence of hole. These holes and electrons can undergo transition described by the Ec diagram. So in this particular Ec diagram, it is, if we consider the momentum along x-axis and energy along y-axis, then you will find for a particular energy there are several values of momentum. So if we consider the electrons exist here and here at the same energy level, then you find the momentum values are different. The energy of electron, which is termed as E, related to its momentum k by the equation, that is Ek equal to a square. It is not a square, it is the reduced Planck constant. H means the Planck constant, and it is reduced one, a square by 2m asterisk. M asterisk, once again, it is not m, that is the mass of the electron. It is m asterisk, which denote the effective mass into k square. Here k is the momentum value, and the H reduced Planck constant is related to Planck constant by this relation, that reduced Planck constant will equal to H by 2 pi. The effective mass is given by that effective mass will be equal to reduced Planck constant square by d square E by d k square. Now if we consider the direct and indirect band gap semiconductor material, then what we find? The maximum of the valence band and the minimum of the conduction band, obviously in terms of energy, those are in the same line. That means if the electrons are moving from the valence band to the conduction band, then what we find, only the energy level changes are there, no changes of momentum. That means in case of direct band gap semiconductor, you find if the electrons are transiting from the valence band to the conduction band, then only momentum value is not changed, only the energy is changed. Now if we consider the indirect band gap semiconductor, then if the energy is of that valence band and the conduction band is like this, that means maximum of the valence and the minimum of the conduction band are not in the same line, then what happens? If electrons are moving from the valence band towards the conduction band, then obviously there will be a change of energy as well as the momentum. That means momentum values are changed if the electrons are moving from valence band to conduction band. If we consider the direct band gap semiconductor, then the example for the direct band gap semiconductor is gallium arsenide or indium phosphide. But if you consider the indirect band gap semiconductor, for that you find the silicon and germanium, those are the popular semiconductor materials, are in this indirect band gap semiconductor category. And these indirect band gap semiconductor materials are not suitable for any optoelectronic device fabrication. The concept already I told you that M asterisk is nothing but the effective mass. Now already it is known to us the mass, but what is that effective mass? If we consider the electrons are inside a crystal and some electric field is applied. Now the case is different when the electrons are inside the crystal and the electrons are in the vacuum. So obviously if the electrons are if an electric field is applied, then under the influence of that electric field we find the electrons will accelerate, but the rate of that acceleration is different from each other due to existence of different potential inside the crystal. So if we consider the electrons in the vacuum, then if electric field is applied, the mass of the electron is given by m0 and it is having the value 9.1 into 10 to the power minus 31. That is the free electron mass. Now if the same electron is inside the crystal, then same electric field is applied, then what will happen to that particular electron? The mass of the electron is on change, and that change mass is called the effective mass. Now we just try to find out that what is the expression for M asterisk. Now particles in electron and holes have an wave number under certain condition. De Broglie postulates are there. By using that de Broglie wavelength principle, we used to link the particle behavior of particles with the wave behavior of particles. So the particles such as electrons and waves can diffracted from the crystal just as X-ray. Certain electron momentum is not allowed by the crystal lattice. The origin of the energy band gaps, if we consider this thing, that is n order of diffraction, lambda the wavelength of X-ray, d that is the difference between planes, theta that is the incident angle of X-ray, then we will find that n lambda that will be 2d sin theta. Now if that sin theta is 1, that is the incident angle of X-ray, if we consider that sin theta is 1, then from this equation we can consider that n lambda equal to 2d. Now here the waves are standing waves, so lambda that will be 2 pi by k, where k is the wave number. What is wave number? In physics, the wave number is also known as the propagation number, or angular wave number is defined as the number of wavelength per unit distance. It is equal to the inverse of wavelength. That means we can write that k that will be equal to 1 by lambda, if that lambda is the wavelength. Already I told you that lambda is the wavelength of X-ray. So here the k is the wave number and lambda is the wavelength. Now the k that will be 2 pi by lambda. Wave number equation is mathematically expressed as the number of complete cycle of a wave over its wavelength, where that k is the wave number, lambda is the wavelength of the wave, and it is measured using rad per m. The momentum, here momentum is defined by p, that will be reduced Planck constant into k. In the de Broglie postulate, the left hand side represents the momentum of the particle, that is p, while k in the right side is the wave number of the wave. The energy of free electrons can be related to the momentum E, that will be p square by 2m. So if you consider that p is equal to h by lambda from the de Broglie equation, then if we replace here the value of momentum, then p square is there, that's why a square by lambda square we used here. So ultimately we will get the E equal to a square by 2m into 1 by lambda square. Now we replace lambda from the previous equation of this, that is k is this one. So from that, if we replace the value of lambda, then we will get lambda is 2 pi by k. After replacing the value of lambda in this equation, then we will get that E will be a square by 2m into k square by 2 pi square. Reduced Planck constant, that is h, this one, that reduced Planck constant and Planck constant relation is h equal to reduced Planck constant into 2 pi. So in place of this Planck constant, we replace it by the reduced Planck constant. Then we will get the value of this one, 2 pi get cancelled, and ultimately E that will be reduced Planck constant square into k square by 2m. To find out the effective mass, we will take the derivative of energy with respect to k, then we will get dE by dk, that will be reduced Planck constant into k by 2m. Once again double derivative of it, d square E by dk square, that is reduced Planck constant square by m. Now here the m, that is change, instead of that m, now we just changing that m asterisk instead of that m, what that m asterisk is nothing but the effective mass. Then if we change this, then from this equation we can write m asterisk, that will be equal to reduced Planck constant square by d square e by dk square. This is the formula for the effective mass of an electron inside the crystal. Now already I told you that is the direct and indirect band gap semiconductor material. So already I told you that is the direct band gap semiconductor material, the minimum of conduction band and maximum of the valence band are in the same momentum value. But if we consider the indirect band gap semiconductor, the case is different. Then the minimum of conduction band and maximum of valence band are not in the same momentum value. So if the electron sitting at the bottom of conduction band recombines with the hole sitting at the top of the valence band, there will be no change of momentum value, and this is nothing but the direct band gap semiconductor. Energy is conserved by means of emitting a photon. Such transitions are called a radiative transition. When an electron and hole recombine in an indirect band gap semiconductor, phonons must be involved to conserve the momentum. So here we came across two terms, that is photon and phonon. For semiconductor which are in the direct band gap semiconductor, we consider the photon one, and if the electrons, the semiconductor materials are indirect band gap semiconductor, then there we consider the phonon. The phonon atoms vibrate about their mean position at a finite temperature. These vibrations produce vibrational wave inside the crystal. Phonons are quanta of these vibrational waves, and phonons travels with the velocity of sound. This wavelength is determined by the crystal lattice constant. Phonon can only exist inside the crystal. If you consider the crystal momentum, in solid state physics, crystal momentum or quasi momentum is a momentum like vector associated with electrons in a crystal lattice. It is defined by the associated with vector k of the lattice and p crystal, that is reduced Planck constant into k. Reduced Planck constant, it is denoted by like this. The quanta, what is that quanta? A particle representing a quantum of light to or other electromagnetic radiation. A photon carries energy proportional to the radiation. Here we find the Maxwell-Boltzmann probability function. The particles are considered to be distinguishable by being numbered, example from 1 to n, with no limit to the number of particles allowed in each energy state. The behavior of gas molecules in a container at low pressure is an example of this distribution. Bose-Einstein function is also there. Then lastly, the Fermi-Dirac probability function. It is very important for you, and here we find that number of quantum states. If you consider the quantum states 1, 2, 3, 4 like that, GI in a particular energy level which is denoted by I, then different quantum states are there. So here that Pauli exclusion principle states that a maximum of one particle is allowed in one or each quantum state, where GI ways of choosing where to place the first particle. If we consider the first particle, suppose G is the particles, available particle states. So if we consider the one where that particular particle is arranged, it may arrange in GI states. But if you consider the second one, then obviously the first position is already allocated for first atom. That's why the other particle that can be arranged in Gi minus 1, so on. If we consider the electron existing in solid, then you find one important formula, that is the Fermi-Dirac distribution function, and that function is given by f of E, that will be 1 by 1 plus e to the power E minus Ef by kT. Okay, this is all about this particular class, which is the first class of your subject. Thank you.